All right. Assalamualaikum. Good afternoon, everyone. Bismillahirrahmanirrahim. Okay. How many of you already in? 14.
Hello, Dr.
Hello. So, yeah, I'm actually waiting for one call coming in within the next few minutes. So if I think let's just start the class for now. Okay. Um. All right. So I need to share my screen. All right. Great. Okay. Um, and where is that thing? Okay. So, and I need to do recording. Okay. All right. Okay. So, this week, basically, we look into another type of algorithm, which is a graph algorithm. Okay, whereby we basically, you can use graph to represent a lot of things, like something like those, like connection, association, network, and then perhaps if, like, let's say you want to represent scheduling or package dependency, so you can actually represent all these entities using graph. Okay, so this week we look at several graph algorithm where you can use to either find search for the element inside the graph, or yeah. So the call came in. I'm so sorry. 1 second. Sorry.
Okay.
All right. Sorry, and I am expecting another one within the next 5 minutes. I'm so sorry. This is what happened when you work from home and there's a lot of things that you have to handle from home. Okay. But
No
anyway,
worries.
so basically, we have looked at several graph algorithm that we can use. So basically, we look at depth first search, breadth first search, whereby you can use this to look for to traverse the graph and visit all the nodes. And then we also look at two algorithm, which we also look at this topological sort, which is an algorithm where you can determine what are the sequence of nodes to visit in order for you to ensure that if, like, let's say there's a dependency, like or prerequisite, let's say for example, you have a path, like let's say for example your course subject, let's say for example, there are some prerequisite that you need to fulfill first before you can actually go to the next subject, let's say for example, or next level. So you can also apply this topological sort using the DFS to actually determine the sequence of which one should be done first. Okay, and then after that we look into two other graph algorithm where you see where you see that we apply the greedy approach, okay, to solve the problem, whereby so far, like for the search based topological algorithm, we don't really look into like any cost or any weight, okay, for the edges, but for Prims and Kruskal, if you remember, we use that algorithm for if, like, let's say you have a weighted graph, weighted edge, okay, and you want to find the minimum spanning tree. Okay, so the spanning tree is those, so a spanning tree is where is a graph, a subgraph of your total graph, whereby it connects all the vertices with v minus 1 number of edges. And that is the definition for spanning tree. Okay. All right. So without any further delay, can we try and attempt question number 1 first? Because I think I think I need to re-explain one of the algorithm that we have during the lecture. But yeah, so can we have the first one? So okay, so we assume that we start from A. Thank you. So we assume that we start from A. So start from A. So basically A, B, S, C, D, E, H, G, F. So you have A. Anybody got a different answer? So here I assume that how you do it is that you will be following alphabetical order. So you're gonna have A. So uh we uh we put in A. And then we can go to B, and then we pop B, and then we include S, and then C, and then D, and then we pop D, and then we put in E, and then we put in H, and then we put in G, H, okay, H, and then you go to G, you pop in G, and then you go to, why you go back to F? Okay, and then you pop F, okay, and then you go into F. All right. Okay, anybody else got a different answer? Okay, so I don't need to take that call. Okay, anybody else got a different answer than this? Anybody have any issues of have no idea how do you actually get this answer? No, you have to tell me. Everybody got the same answer.
What is that diagram at the right?
The diagram on the right, this stack status.
Yeah. Is that like, just to illustrate a stack or cube, is it?
No, actually, if you write it faster, you can actually, like show the, how do you call that? The stack status. Okay, so, but the stack status, in fact, the stack status, is changing, right? So whenever you, put in the A, and then you pop out the, pop in the A, and then you pop out the A. So basically the changes in the stack is actually like you should have like a series of stack status, but then you can also do it something like this. Okay, stack will look like this, and then basically you have pop, and then supposedly the status by end of the after finishing the depth first search, your stack should be empty. Okay, so in a sense, here you pop B, you insert B, and then you pop, and then C, D, and then you pop D, and then you enter E, H, G, F, and then supposedly you should pop F, pop G, pop H, pop E, pop C, pop S, and finally you pop out A. Okay, so in the end, your stack status should be empty, which will tell you that you have finished visiting all the nodes. All right. Okay, so anybody else got a different answer? So we assume that we take it as alphabetical order. Okay, so if you do this, so you should be getting the same answer as this one. All right. Are you all right with this one? Should be okay, right? Okay, so for question number 2. Please tell me the reason why I don't explain it. What is because then you can always refer back to the selection. Okay, so the queue would look like okay. So question number 2 is breadth first search. So basically the difference between the depth first search and the breadth first search is that for the DFS it is using stack, and the BFS it is using queue. All right. So we start from A. So the queue would look like you put A in, and you queue B, and you queue S, and then you DQ A. Okay. And then you DQ A, and then you look at B, and then you DQ B, and then you look at S, U, Q, C, and G, right? And then you look at S, and U, Q, C, and G, and then you DQ S, and then you look at C, and then you Q, D, E, F, and then you DQ C, and then you look at G, and then you Q, H, and then we are done. So supposedly after the H, you should be DQing the rest as well. Okay. So you should get A, B, S, C, G, D, E, F, H. Okay. Meaning the queue should have that sequence. All right. Anyone else got a different answer, or have no idea what's happening? For the breadth first search, we can assume that we are searching it level by level. Okay, so for the DFS just now, we sort of like looking. We go down first before we go up, and then look at the other branch. Okay, but for the breadth first search, it's like you start from basically your starting point is the first level, and then you go to the next level, you look thoroughly onto the second level, and you go on and you move on to the next level and the next level. All right, so that is the difference between the DFS and the BFS. Okay. All right, no question, right? Should be okay, right, this one? All right, so for question number 3, so this is a topological sort where you want to find out what are the sequence. Okay, so if like let's say we assume that A, F, E, B, C, D is packages or libraries that are dependent with each other. So let's say for A, in order for A to work, you need to have F and E available, or maybe you're talking about scheduling, in order for you to execute B, or event B to occur, you need to have event E and D occurred before B. So it can be a those kind of representation, and you want to find out which one should you execute so that you can complete the execution. Okay, you don't need to actually like like being delayed because the whatever requirements is not available. Okay. So for this topological sort, we're going to be using the DFS for us to determine the sequence. And I'm so sorry again. Tuesday, my brain, I have no idea what happened to my brain. I think it's because it's seriously crazy on Tuesday. And I'm probably going to explain to you again how we can do this. But for those of you So for those of you who have like try and do it, can you share me your answer? What are the possible sequence that we can have for this one? Class?
Yeah, this one I don't really understand. Oh,
Yeah. I have one sleep. I cannot sleep that night because I remembered. I think I was like I don't know what I'm talking about during election.
don't
So
worry.
yeah. So anybody who sort of like refer to a different place and try to do this one? Class? No? No answer? Nobody attempted? Nobody look for different resources on how to do this? No one? No? I have 21 in class, so uh, but yeah, I did notice that there's a few video that is a little bit confusing. In fact, the one in common, if you look into the common book, they don't really the example that it give, it's just mentioned that the sequence they have like, if you remember inside the slide we have two, right? Example, one is the one without the weight at the edges, and then we have that how do you put on your clothes, the sequence, and then you have the starting time and the end time. So basically from the common book it already mentioned that those times are acquired from applying the DFS into it. So all you have to do is just arrange the sequence based on the end time. Okay, so I know it's a little bit confusing, and the first example, actually, I mentioned that you need to you basically you apply DFS, and you will get the sequence based on the stack itself. Okay, so but not I remember I said that you the sequence is based on the stack, but it is actually I should be more clearer that the sequence is actually based from the sequence where you pop out. You know, like whenever you pop out the thing, that would be giving you the sequence of possible of a possible sequence for that graph. Okay, so anybody wants to try it first? Do like a normal DFS, like choose any nodes, do depth first search, apply the depth first search, um, um, and then until like let's say for example you start from what, so basically if whenever the stack is empty, you go and look for another node and you do again the DFS until all the nodes are visited. Keep track of what element that you pop out, that will give you the sequence. Can do you want to try first, or do you want to do it with me? Then it'll be no fun. You know the DFS already? Okay, so somebody is giving me this. So start from F. Okay, so the stack is F, A, pop A, and then you go back to F, you got C, D, B, yep, and then you pop B, you pop D, you pop C, and you pop C. Why you haven't pop F before your E? So topological sort. So you need to pop F, and then you E, and then pop E. Yep. So basically be A, B, P, C, F, E. You got it? Is that right? That's one way of doing it. Anybody have any question about this one?
Thank you, Fahad.
Got it, right? Okay.
Got it.
Yeah. So basically, you do the DFS just like DFS. So basically, the sequence will be you will get the sequence based on the when you pop it out, and then you will see that this will be the sequence. So actually, this one is actually reverse. It's supposed to be but basically, if you draw this and the arrow, you will see that all the arrow is going to be the other way around. But then it's a reverse order. So you need to do E first, F, C, D, B, then A. Can you because if you see that if you draw this if you draw back the graph with the arrow, it is actually going backwards. So you need to reverse the sequence. The order is correct. It's just that it's reverse. So you need to do E first, and then F, and then C, and then D, and then B, and then A. You get what I mean? Class?
Yeah, got it.
Yeah. So supposedly the sequence is reversed. The order is correct, but sequence is supposed to be reversed. Okay? Anybody else got a different answer? Anybody else got a different answer? No one? You're not trying? No one? Oh dear. How many people inside my Google Drive? 11. No more? I have how many variants? I have 1, 2. I can get at least 3 different sequence. Nobody else got a different sequence than this. Can someone try? Are you trying? Or should I go to the next question? Oh my god, I miss the normal classroom. And then you cannot like hide. I can just walk to your table and see whether you're doing it. Like this is like, I feel so like. Are you going to give me another answer? Okay. Yeah, you have a question. Come, just ask. You better ask now than later. You're quite lucky that you don't like have a final exam. So normally these are whatever things that you do during your tutorial is normally the kind of question that you're going to see during your final exam. But since I think our final exam, we change it to individual report. So yeah, so basically, that's why during the tutorial, I want to emphasize on the application to ensure that you actually know how to apply it. And trust that you actually do your tutorial and actually get the knowledge, because if you just listen to the lecture or you just reading it, so yeah, you know something about it, but you're probably gonna have you're gonna have some problem if, let's say, for example, you want to try like apply it on some example. Okay. All right. Okay. So I just leave it to this one. Basically, in order for you to check whether your sequence is okay, all you have to do is just try to connect the edges, okay, to see whether is there any cross is there any arrow that is going the other way around. Okay. All right. So that is for the topological sort. I got confused during the lecture because I saw another way on how to explain it, but somehow I got confused. So I think I better stick to how I used to explain it. So I guess this would be much easier for you to see. Okay. All right. So for question number 4, so as you know, graph, you can represent it either using the adjacency list or adjacency matrix. Okay, apart from the diagrammatic graph that you do, basically you have nodes and edges. Okay, so here, you have been given the adjacency list. For A, you need to draw the directed graph. For the adjacency list. Okay, so we have A going to B, going to C, going to D, B going to A, C going to B and D, and we have D. Okay, anybody got a different graph? This is a directional graph because as you can see, the edge have arrows and the nodes have label. There's no weight to it, okay? But yeah, so this is the graph that you're supposed to get based from this adjacency list. Anybody got a different answer? No? Please quickly let me know if you have a different answer than what has been given by your friend. Right? No? No. Okay. All right. So I assume that all of you are good. Okay. And then for B, you need to all right, great. So basically, for B, you need to represent it using adjacency matrix. Yes, do you have any question? All right. So for the adjacency matrix, so B, C. So from A, there's a B, C, D. B goes to A. C goes to B and D. C going to B and D, and D is all 0. Okay. So all right. So these are the type of representation that you can do for your graph. Okay, either you do a diagrammatic representation, visual representation as such. So or you can do, let's say for example, you want to implement graph. You may represent it using list, okay, linked list, or some kind of multi-dimensional array. Okay, so as I mentioned during lecture, each of these representation has its pros and cons. So it depends on the type of application that you're going to be using. If it has frequent accessing information about the nodes, then perhaps adjacency matrix is much more appropriate because the access time is constant. All right. But for the adjacency matrix, the drawbacks is that if, like, let's say, your application requires you to add and remove nodes, then the running time complexity is going to be v squared. Okay, because if you see here, if let's say we add another node, you need to add another a row and column of array, okay, to represent the graph. So therefore, the adjacency list will be much more better if you have the add and delete, because all you have to do is just append it to the end of the list or delete the list and reconnect the linked list and everything. It's just that for the adjacency list, if you want to search, then perhaps it's going to take an extra time because you need to traverse the list. Okay. Yeah, and then and then I saw this. You have a different two more answer. So you have F, C, D, E, A, B, right? And then you have F, uh, F, E, C, D, B, A. Yeah. Can F comes first before E? This one is wait, you put F. Okay, supposed to be EF. Yeah. Okay. So this one is okay. Can you check this one, class? F C D E A B. So this one is okay. This one is okay. So the other one is F. Oh, sorry. This one is F E C D B A. So mm, okay. So this one is also okay. All right. Oh, sorry. The second answer is also okay. Okay, so these are the variants of answer that you can have for the topological sort. All right. Okay. Okay. Up until now, are you good so far? Right. Okay. So up until now, all the graph that we looked at does not have the cost. Okay, the edge does not have the cost or weight. Okay, to it. So basically, all the first two, the DFS and the BFS, is an algorithm for you to traverse your graph or search for an element. Okay, or print out whatever element that you have inside your graph. And then for the topological sort is if you want to determine which sequence, if let's say you have a prerequisite or dependencies, then you can use that to compute what are the order for the nodes to be available. Okay. So next, we are going to look at the MST. Okay, we look into spanning tree, whereby we want to find out what are the minimum, not minimum. Spanning tree is more. Spanning tree is a tree, a subtree from your graph that will connect all your vertices with v minus 1 number of edges. Okay, so the smallest number of possible edges that connects all vertices, okay, from the graph. And basically from a graph you may get a lot of spanning tree, but and then but then if like let's say your graph have a cost, then the cost may be different. Even though the spanning tree is a subtree of the graph, but the cost may be different. Okay, so in this case, our problem is that we want to find what is the smallest cost of spanning tree that we can get out of this graph. And there are two ways of you two ways that you can do. Okay, in order to find what is the minimum spanning tree. So and then for the to find the minimum spanning tree, we have looked into two algorithms that uses the greedy approach. One of the algorithm grow the spanning tree. They only grow one spanning tree, and the other one grow the spanning tree by connecting branches. Okay, a forest of branches. Okay, So let's look at the first one, question number 5, where you are asked to find the MST using the Prim's algorithm from vertex A. So this Prim's algorithm, how do you grow your tree? So basically the tree, yeah. How do you grow your tree? Is it like single tree or forest? Prims?
I think it can be forest, right? Is it? Because you're supposed to find edges that connect the tree to new vertices.
Okay. As I mentioned just now, the difference between Prims and Kraskell, one of them only grow one tree, and the other one, you sort of like have like you may have some branches here, some forest here, and then but basically you will end up with one minimum spanning tree. So the way that they add the safe edges is different. So one, they add it into one tree. So they just grow the tree from one place and then it just keep growing the spanning tree. And the other one is like you have this, you have that, you have that. So you add the safe edges, but the edges are not necessarily connected with each other. But they will end up giving you the single spanning tree. So the Prims one, is it that you grow the one with only one tree or the one with the forest where you get like a bunch of small trees that will build up and will be eventually connected to make the spanning tree?
I would say the former, right? Right.
For the Prims, which one? What did I say for the first one?
The one that's
One
not
tree.
forest.
So for the Prim, you only build one tree. Okay, so can someone give me what are the costs? Or maybe I don't know this one, but just now I just asked for what are the costs of the edges that you have chosen from this one.
Wait, I don't think you're asking course, eh?
The cost, the total length.
Oh, okay, so
So the question for B, total length. Okay, so you just, since I don't know how, or anybody draw the spanning tree already? So you just add 59. What are the what are the value that you add?
wait, so we start from A and then
Okay. All right. 59. Right? So so A 5, 8, 9, 19, 12, 1, 2, 3, 5. Right. Yep. Anybody got a different answer? For this one, it's not I don't think it's possible for you to get a different answer because it looks like all the edges does not have much duplication. Maybe 8 have duplication. So there's not much how do you call that, variety of spanning tree that you can get. But yeah, so you should be getting the same answer for this one. It's quite impossible for you to get a different answer because of the way that the edge is being, the cost of the edges for this graph. Anybody got a different answer? I guess that should be the most appropriate question, rather than if you have any other question, any other answer. Anybody got other, do not get this answer for this one? Or or you don't know how to get this one? No? All good? Really? Okay. So So basically, what you do for this one for prims, as we discussed just now, for prims, how they add the safe edges is that you check all the possible edges that is coming up from the already of the spanning tree that you're growing. Okay, so if like let's say we start from A, so basically the edges that we are going to be considering is 5, 8, and this 8, right? Oh yeah, you can actually have a different oh no, because we choose 5 first, right? So we choose 5 and we add this edge into the spanning tree. So this would be the first edge that we add into the set. And then the edge that we consider next would be 3, 2, 4, 8, and this 8 as well. So we're trying to see which have the smallest value. So this would be the next edge that is added to the spanning tree. Okay, so that's why you have this, and then you have this one next, and then you add you consider all the edges that is connected to A, D, and H. Okay, all the adjacent nodes that is connected to all the nodes that is already included into the spanning tree, and you keep doing it until you have included all the nodes and the edges is there's no you're not supposed to have a cycle inside your spanning tree, and the number of edges is v minus 1. Okay, and then you total up the cost and you're gonna get 59. So 5, 3, 8, 10, 11, 19, 28, uh 38, 30, 59. Okay. All right. So for finding minimum spanning tree using cross curls, same thing. It's just that for cross curl, you sort of like find which smallest edges that you can add uh, to the set. Okay, so the set may not be connected with each other, but how you add the same edges is that you look at the graph and you choose the smallest edge every time to add into the set while making sure that there's no cycle. Okay, so in this case, the smallest edge that we are going to add is this one, BC. So the next one would be this one, EF. Okay, so the first safe edge is this one. The second safest safe edge is this one, right? And then this one, right? BA 4, and then we got 5. We add this one in. 5, and then we have 6, right? Still okay because it's not a cycle, so you just add it in. It's safe to be added to the MST. 6, and then 7, right? BE 7, and then you got 8, right? Is it safe? Yeah, it's safe. And then we got 9, right? We add in 9, and then 10. So 10 DE. So here we cannot add this, even though this is the smallest. DE is the smallest edge after currently. We cannot add this into our MST set is because you are going to create a cycle. So we're going to go look at the next smallest cost edges. Is 11, DG. DG also we cannot take that edge because it is going to create some kind of cycle, right? This one. 11, and then 12. Yeah, so we can add this one safely. 12, right? And that's it. We have covered all the notes. So total up the cost. So 3, 7, 12, 18, 35, 33, 41, 44. Okay, so the cost is 54. All right. All right. Anybody got a different answer? Should be okay, right? This one, right? No answer? No answer. No, no question. No question for this one, right? So we're gonna this week is quite a short one. I plan to actually create an asynchronous just create a video for the next lecture. Uh, but then I think better it's better that we use next week to go through the next lecture as well as the tutorial. We try to do dynamic by week 13. Um, and then because week 13 you probably just going to be given like some kind of reading in regards to multi-trading. I don't think we are going to do any tutorial on that, but from we got feedback from those going to internship. It looks like there are companies that actually uses multi trading. Okay, so I don't know, but in my opinion, I guess, and then multi trading, you probably for I think for software engineering students, you're probably going to be having this when you are doing which course are that elective course. I don't remember what elective course. One of the elective course you will have to implement a lot of threads. I don't remember what is that course name, the elective. So you're probably gonna be doing that in the elective course. So I guess it is semi-important. And it's good for semi-important is just a word as that. So so in a sense, it is good for you to know something about it. Okay. All right. Okay. Um, no more question about this, and then we can end our tutorial for today. You can use the time, this extra time to complete your group project because week I will start opening slots from week 13. Okay, in case some of you have already completed and I want to get rid of that assessment as soon as possible. You'll be doing your peer assessment. I think maybe I will give you the form starting next week where you have to fill up the form. All right. And your individual project will be published in week 13. Okay. And then you have to submit in week 15. So again, for those of you, you can always like submit it early. And I think the individual project is not that difficult. It requires you to just read and understand the article. Okay. Um. And it's very yeah, I don't know, but yeah. Uh, just go and look at individual assignment later, and then you will see what you should do then. Okay. Yeah. So if there is no more question, can we end the class for today? Huh? Class?
End of
Yes. Okay. So I guess I'm going to see you next week. We're going to be looking at part 2 of the graph algorithm. All right. So let me stop recording first. And yeah, so I guess I will see you next week then. Right? Bye. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, doctor. Bye.
Thank you.